Today we'll be talking about normal modes of a fuel sender flange used for automotive applications. As part of this study, we'll first verify the performance of the finite element used for the fuel sender flange model, and then we'll do a finite element modal analysis of the fuel sender flange. And finally, we'll compare the finite element modal results with experimental modal results. This is the fuel sender flange that we'll be examining, and notice that it's about 180 millimeters long, 36 millimeters wide, and about 1.5 millimeters thick. This fuel sender flange fits into the fuel tank for an automotive application, and the pump is mounted in this general area here. The fuel sender flange is modeled using shell elements. There are 4-node shell elements, and we'll see how well that element performs before we look at the results of this model. The first part of the case study concerns verifying the shell element performance. To verify the shell element performance, a closed-form solution to a cantilever beam was developed. The finite element analysis of the cantilever beam was then performed, and the results of the closed-form solution and the finite element analysis were compared. The reason for doing the verification testing is just to gain some familiarization with how the shell element performs under a known condition. Let's examine a cantilever beam, a simple cantilever beam, to derive the closed-form solution. And we'll use that closed-form solution again to compare the performance of the shell element to a known structure. The cantilever beam has an axis, longitudinal axis, x, and the displacement in that direction is denoted as lowercase u. The transverse axis is the y-axis, and displacements along that axis will be denoted as v. The cantilever beam has some force per unit length applied to it, and we'll be interested initially with a small portion of the beam of an infinitesimal size dx. To develop the closed-form solution, we'll assume that the summation of the forces in the y direction are equal to mass times acceleration. And also, looking at the small slice of the beam, we'll assume that the summation of the moments is equal to the mass moment times the angular acceleration. But in this particular case, we're going to assume that the summation of the moments is equal approximately to 0. And the reason why is we're going to apply this formula to a shallow cantilever beam. It's not very deep. And so we'll assume also that the frequencies will be low. And in for both of those conditions, then, we can assume that the angular acceleration will be small enough so that we can assume that the rotational moments are approximately 0. Let's examine the differential slice of the cantilever beam to develop the closed-form solution. Summing moments about point O, we note that we have a shear force on the left, a moment on the left, a distributed force in units of force per unit length, and a resisting moment and another shear force on the right-hand side of the slice. So summing the moments about point O, and the moments will be summed around the z-axis, we note that we have m plus v dx, the quantity minus the quantity m plus dm, that's the moment on the right-hand side, plus the quantity f dx times dx over 2. And where that term comes from is we have a force per unit length times dx, so that gives us a force, and then we have a moment arm of dx over 2. And we set that equal to 0. Now if we note that dm is equal to the partial of m with respect to x times dx, and we discount second-order terms in the equation, we see that v, the shear force, is equal to the partial derivative of the moment with respect to x. Or, if we take the derivative of both sides of this equation, we find that the derivative of the shear force is equal to the second partial derivative of the moment with respect to x times dx. Returning to the differential slice, we now sum forces in the y-coordinate direction. And we find that F dx plus the shear force minus the shear force on the right-hand side is equal to the inertial force. And the inertial force is a function of rho, which is density, cross-sectional area, and the differential dx. And also an acceleration term, the second derivative of displacement with respect to time. Recalling from the other slide that dv is the second partial of m with respect to x dx, and simplifying, the equation above results in these three terms. F minus the second partial of m with respect to x is equal to the inertial term rho a second partial of v, and that's displacement in the y-coordinate direction again with respect to time. For a slender beam, we normally call them Euler-Bernoulli beams, we know that the moment is equal to EI times the second partial of displacement with respect to x. So using this in the equation above, we find that F minus the quantity here is equal to the inertial term. And for a uniform beam, we know that EI is constant, such that the second partial of this quantity can be performed, and we find that F minus the quantity EI times the fourth derivative of displacement with respect to x is equal to the inertial term. Returning to the equation for the summation of forces in the y-coordinate direction, we arrange the terms as such. We have an inertial term with density, cross-sectional area, second derivative of displacement with respect to time, plus an elastic force, EI, times the fourth partial of v with respect to x, and again v is the displacement in the y-coordinate direction, and we set that equal to the applied force. However, for free vibration problems, F, the applied force, is set equal to 0, such that the equation above contains two terms. One is the inertial term, and one is the elastic force term. We can also state this equation as the inertial term is equal to the negative of EI times the fourth partial of v with respect to x. In other words, the inertial term is equal to the negative of the elastic term. And for free vibration then, we might think of it as the inertial terms balancing the elastic forces. Returning to the differential equation, what assumptions were made? We assume that there is no rotatory inertia and that transverse shear deformation is approximately 0. We also assume that the beam under consideration is slender and uniform. For uniform beams, the product EI is constant along the entire length of the beam. We can solve this differential equation by applying appropriate boundary conditions. For a cantilever beam, the fixed end of the beam has a slope of 0, and also transverse displacement is equal to 0. So using those two boundary conditions, we can solve the differential equation, and we find that the frequency is equal to k sub I times the square root of EI divided by rho a L to the fourth. EI, again, is the stiffness of the beam, represents the stiffness of the beam. E is the elastic modulus. I is the second moment of the cross-sectional area. Rho is the density. A is the cross-section, and L is the length. We find that for each frequency, we have associated with it a constant k sub I. So plugging into the equation, substituting into the equation, each of the constants, we can calculate the frequency for each mode shape. We now have a solution for the differential equation that describes frequency in a cantilever beam. Let's use that equation for a simple cantilever beam model. The cantilever beam that we'll look at will be considered in two orientations. In orientation 1, we have a thickness of 1.32 millimeters. In this orientation, I'll call a diving board orientation. In orientation 2, we flip the beam onto its side, and now the depth becomes 36 millimeters. So in this orientation, orientation 2, the beam is much more stiff than in orientation 1. And since frequencies are driven by stiffness, we should see quite a bit of difference in the frequencies between these two orientations. Also note that the dimensions of this cantilever beam that we'll be looking at are roughly of the same order as the fuel sender flange. Using the closed form solution for the cantilever beam, we find that in orientation 1, the first mode, the frequency is 33.9 hertz. Orientation 1, second mode, the frequency is 212 hertz. Orientation 1, third mode, 594 hertz. And orientation 2, remember that's with the beam flipped on its side, mode 1, the frequency jumps up to 923 hertz. As we thought, as we suspected, since in that mode the beam is quite a bit more stiff. Now, these are the closed form solutions for a simple cantilever beam. Let's test the finite elements to see how close we can come to the closed form solution. For our first finite element model, we'll try 10 elements. We computed frequencies for the simple cantilever beam. Now let's use a finite element model to see how well the closed form solutions compare to finite element results. The finite element model is 36 millimeters wide, 180 millimeters long, and 1.32 millimeters deep. The first finite element model that we'll use uses 10 shell elements, and the elements are fixed on the left end to simulate the cantilever beam condition. We'll perform the finite element analysis now using what's called finite element modal analysis and find out how well the results compare. We now have closed form solution and finite element results for the cantilever beam. Let's see how they compare. In orientation 1, mode 1, the finite element model predicts 34.6 hertz. This compares favorably with the closed form solution of 33.9 hertz. Orientation 1, mode 2, FEA predicts 238 hertz, while the closed form solution predicts 212. Again, pretty good correlation. We have some other modes. I'm going to mark them as question mark modes for right now, and we'll get back to those later. Orientation 1, mode 3, FEA predicts 812 hertz, but the closed form solution predicts 594. So now we see there's a slight difference between, or somewhat of a difference between the two results. And we'll discuss that in a moment. Orientation 2, now that's the stiff orientation, mode 1, FEA predicts 924, and that compares favorably with the closed form solution of 923. We also have another one of these question mark modes, and I'll talk about that in a minute. But first of all, why the large error in orientation 1, mode 3? We noticed that there was somewhat of a difference between the closed form solution and the finite element results for orientation 1, mode 3. Let's see if we can determine why there was an error. Looking at the finite element model, using 10 shell elements, we find that the shape of the mode is not exactly smooth. In other words, this isn't something that we'd expect to see in nature. The mode shape of the cantilever beam for the third mode should be roughly a sinusoidal shape. So the question is this mode shape well represented with using only 10 elements? We noticed that although the lower mode shapes corresponded well with the closed form solution, the higher mode shapes started to become more and more errant. Specifically, orientation 1, mode 3, the frequency was off by quite a bit compared to the closed form solution. What can we do about that? Well, we noticed that using 10 shell elements, the model did not represent the mode shape very well. As we increase our finite elements, we might expect the results to become better. Now we look at a finite element model using 60 shell elements, and notice that the mode shape more closely represents a sinusoidal function. We can expect then that the frequencies will be closer. We notice that using more elements, the mode shape more closely represents the actual mode shape. And we'll compare frequencies in just a minute. But a few notes first. We can often use fewer elements for a modal analysis than for a stress analysis. But the frequencies may be incorrect if the mode shapes are not properly represented. And finally, it's often difficult to represent higher frequency mode shapes with a coarse mesh. And that's what we found in our simple model. Using 10 elements, the higher mode shape was quite difficult to represent, although the low mode shape, the frequency was quite close and the mode shape was fairly correct. We found that increasing the number of shell elements helped the mode shape more closely represent the closed form solution mode shape. Now let's take a look at the predicted frequencies of FEA and compare them to the closed form solution. In orientation 1, mode 1, with 60 finite elements, we find that the frequency predicted is 34.3 Hertz. The closed form solution predicts 33.9. Orientation 1, mode 2, 60 elements, FEA predicts 217 Hertz. The closed form solution is 212. The next mode is a question mark mode, and we'll talk about those in just a minute. The mode we had a problem with, the mode shape we had a problem with trying to accurately represent using 10 shell elements was mode 3. Using 60 finite elements, we find that the frequency predicted is 622 Hertz, and the closed form solution is 594. Notice that with only 10 elements, the frequency is 812 Hertz, quite a ways off from our closed form solution of 594. But using 60 elements and getting a better representation of the mode shape, we're not too bad. The frequency compares favorably with the closed form solution. In orientation 2, that's the stiff orientation, mode 1, with 60 elements, we find that the frequency predicted by the finite element model is 904 Hertz, and the closed form solution is 923. My question is, what modes were not accounted for using the closed form solution for beam bending? We notice that the finite element model predicts modes that aren't accounted for by the beam bending solution. What are these modes? Well, they're torsional modes. Remember that the closed form solution only predicts beam bending modes. What does the torsional mode look like? Well, the first torsional mode appears to be a twist down the longitudinal axis of the beam. We found that the finite element model predicted torsional modes, but these modes weren't accounted for using the closed form solution for cantilever beam bending. Can we develop an expression for torsional modes of a cantilever beam? Yes. Let's begin with a circular shaft of length dx, and we'll observe that there's a moment on the left end of the shaft, a resisting moment on the right, and an externally applied moment to the top surface. The shaft rotates through an angle theta with the moments applied. If we sum moments of the shaft, we find that on the left end we have a negative moment plus the externally applied moment per unit length plus the moments on the right, and those are set equal to the inertial term, the angular acceleration times the polar mass moment of inertia. Let's return to the details for the equation of motion for torsional vibration of the cantilever beam. Using the relationship dm is equal to the partial of m with respect to x dx, and rearranging, we find that f plus the derivative of m with respect to x is equal to j naught times the second derivative of theta with respect to time. Using the relationship m equals gj d theta dx, we find that the equation becomes f plus the quantity of the derivative gj d theta dx is equal to a naught second derivative of theta with respect to time. Assuming a uniform shaft, gj, which is the torsional stiffness, is constant, and for free vibration, the externally applied moment, F, is equal to 0. Using these in the equation above, we find that GJ, torsional stiffness, times the second derivative of theta with respect to x is equal to J naught d theta, second derivative of theta with respect to time. And again, free vibration occurs when the elastic forces, described by the left-hand side, are balanced by the inertial forces on the right-hand side. We'd like to determine the torsional vibration frequencies for the cantilever beam. We can do that by using the closed form differential equation that we developed on the earlier slide and applying boundary conditions. On the left hand of the cantilever beam, the beam is clamped, and on the right-hand side, there's no applied torsion. We find that using these boundary conditions, the frequency for torsional vibration of the cantilever beam is 2I plus 1 over 4L times the quantity square root Gj over J naught. And I takes on the value 0, 1, 2, and so on, depending on which mode we wish to calculate. J naught is the polar mass moment and is equal to I sub y plus I sub z. Gj is the torsional stiffness, and for circular shafts, Gj is equal to G times r to the fourth over 2, where r is the radius of the shaft. For rectangular shafts, or beams, we have to use a different equation. Gj is equal to G times beta a cubed b. And we can look up the value of beta in some tables that are provided by Timoshenko. So using the rectangular torsional stiffness equation in 3, we find that the frequency of our rectangular beam is equal to 2I plus 1 over 4L times the quantity square root G beta a cubed b over rho I sub y plus I sub z. And again, I takes on the value of 0, 1, 2, and so on, depending on which mode we are calculating. We found that the cantilever beam vibrates in a bending mode and also in a torsion mode. We developed closed-form solutions for both of these modes to determine what the frequencies are. Let's compare those frequencies. In orientation 1, mode 1, the finite element model with 60 elements predicts 34.3 Hertz, while the closed-form solution predicts 33.9. In orientation 1, mode 2, the finite element model with 60 elements predicts 217 Hertz, while the closed-form solution predicts 212. These are the new modes that we're calculating now, the torsional modes, the ones that we initially did not consider. The first torsional mode, the finite element model with 60 elements predicts 344 Hertz, while the closed-form solution predicts 325. Let's skip these other two modes. We've already reviewed them in the other slide. And look at the second torsional mode. The second torsional mode, the finite element model with 60 elements predicts 1057 Hertz, while the closed-form solution predicts 975. Overall, it's seen that the shell elements perform pretty well for cantilever beams in bending and torsion. So far, what we've done is examine the performance of shell elements. We found that for a cantilever beam, the shell elements perform fairly well in bending and torsion. But our primary objective in this case study is to look at a fuel sender flange for automotive applications. What we'd like to do is a finite element modal analysis of the fuel sender flange and then compare that to experimental modal results. Before we get into finite element modal analysis, let's take a look at the equation of motion for a simple single degree of freedom system. We have, for a single degree of freedom system, mass times acceleration plus damping times velocity plus stiffness times displacement is equal to some externally applied force. And I've used the notation x dot is equal to the derivative of x with respect to time. Now if we assume no damping and free vibration, the equation above becomes mx double dot plus kx is equal to 0. In other words, mass times acceleration plus stiffness times displacement is equal to 0 for free vibration. Returning to the equation of motion for a free, undamped, single degree of freedom system, we find that the inertial term plus the stiffness term is equal to 0. We know that the differential equation of this form has a solution of the form x times sine omega t plus theta, where x is the amplitude. We can substitute this known form into the differential equation and rearrange and find that the inertial term plus the stiffness term is again equal to 0. We can simplify this equation and find that k minus m omega squared times x is equal to 0. In other words, the stiffness minus the inertial term times quantity times the amplitude is equal to 0. And the non-trivial solution for this equation is that omega is equal to the square root of k over m. And the trivial solution, the one that we don't really care about, would be is if the amplitude was 0. That would also be a solution to the equation. But what we really want to know is what is the frequency of vibration for this simple single degree of freedom system. We developed a closed form solution for the frequency of vibration of a simple single degree of freedom system. With only 1 degree of freedom, and considering the positive roots only, we have 1 frequency of vibration. However, finite element modal analysis considers systems with multiple degrees of freedom. And the equation for multiple degrees of freedom with an undamped, free vibration system would be mass times acceleration plus stiffness times displacement is equal to 0. However, in the case of finite element analysis, these values are matrices or vectors, not simply scalar values. So the displacement for a multiple degree of freedom system is a vector quantity. In other words, displacement x is a vector having an amplitude vector times the sine of omega t plus theta. So if we assume that is the form of the solution for this vector equation and we substitute in, we find that k minus omega squared m quantity times x is equal to 0. Now this equation is quite similar to the scalar equation, except that the variables inside are now vectors or matrices. We have the equation of motion for a multiple degree of freedom system. The system is undamped and is considered free because there's no external forcing function. We can solve that system of equations, and the solution becomes the form, the determinant of k minus omega squared m is equal to 0. How many roots are there to this equation? How many solutions are there for frequency? Well, the number of solutions are equal to the number of degrees of freedom in the system. And we also note that the solution for frequency is independent of amplitude. In other words, the equation given does not have the amplitude term in it. Then what significance then are finite element modal amplitudes? Well, actually, the finite element modal amplitudes should be used for comparison only. They do not give exact numbers. They're only used for relative comparison. The solution for the multiple degree of freedom system is used by the finite element method to predict modal frequencies. In this study, we used those equations with the IDEAS, SDRC IDEAS code and the MARC finite element code to predict frequencies of the fuel sender flange. And now we'd like to compare the finite element predicted results with experimental modal results. Experimental modal analysis of the flange was performed, and to perform experimental modal analysis, the structure is given some type of excitation, either by an impact hammer or perhaps a shaker. The response on the structure is measured with accelerometers, and frequencies are computed. So after the experimental modal was performed on the fuel sender flange, we compared those values, those results, to the modal analysis that was performed using the finite element method. We now have results for vibration of the fuel sender flange by 2 different methods, the finite element method and experimental modal analysis method. Let's compare the results. In the first mode of the fuel sender flange, the mode shape takes on what is primarily a first beam bending shape. The finite element model predicts 32.9 Hertz, and the experimental model predicts 35.5. The error is roughly 7%. The next mode of the fuel sender flange is somewhat torsional, appears to be basically a torsional mode. The finite element model predicts 116 Hertz, and the experimental predicts 114, with an error of just roughly 1%. The next mode of the flange is what is primarily a bending mode. Looks essentially like second bending mode of a cantilever beam. The FEA predicts 178, while experimental predicts 166, and the error is about 7%. I won't go through all these, but it is interesting to note that the error is roughly plus or minus 10%, except for mode 5. The finite element model predicts 432 Hertz, while the experimental results predict 305 Hertz. And it's obvious that the experimentalist must have made a mistake, because, as we all know, finite element method is always correct. I'm just kidding, of course. I'm not certain why there's a variance there, but there is a variance of roughly 42%. But all the other modes are basically plus or minus 10% between experimental and FEA. It's interesting to note that the first mode of the fuel sender flange experimentally determined was 35.5 Hertz. Now, if we consider the fuel sender flange to be just a simple cantilever beam, and we use our closed form solution with the dimensions of the fuel sender flange, we predict a closed form solution for the simple beam of 33.9 Hertz, which compares quite favorably with the experimental results and, of course, with the FEA results. Point being, if one was only going to compute the first mode of this fuel sender flange, there wouldn't be much need to do the experimental or the FEA. A simple closed form solution might be all that's needed. Of course, in the higher modes, if we're interested in the higher modes, that the closed form solution is not really applicable because of the geometry of the flange. But just for that simple first beam bending mode, we do predict fairly closely. So we've compared the response of the fuel sender flange using three different methods, essentially: finite element method, experimental modal method, and for the first mode, a simple closed form result. Now, typically, experimental methods are considered to be perhaps more accurate because we have the actual part in front of us, and generally in industry, experimental methods have typically been accepted better than analytical methods, because it's thought that with the physical part available, all we need to do is properly interpret the results. Whereas using analytical means, generally we have many engineering assumptions that are thrown into the analysis, and in each case, each assumption has a tendency or a chance for error. So again, all three methods have their place, and the good analyst is able to use all of them or one of them or any combination of them depending on the particular situation. Let's take a look at the results for the fuel sender flange. The first mode, as I stated on the earlier slide, is basically bending. It looks a lot like the first beam bending mode. We are reviewing the mode shapes from the analysis of the fuel sender flange. The second mode, predicted by finite element analysis, is mostly torsion, and it appears to be twisting the bottom of the flange, while the top of the flange, which is fixed by the fuel tank, remains basically stationary. We're examining the results of the finite element analysis for the fuel sender flange. This is the third mode, and the mode shape looks basically like the second mode of a cantilever beam. Note that the left end of the fuel sender flange is fixed, while the right end is free to move. The color contours represent the maximum displacements of the structure. This concludes the case study of the fuel sender flange. The work done here is representative of some of the work I've done at Ford Motor Company. I'd like to thank Professor Anderson for being able to participate in this lecture series. Thank you.